Let us start the second lecture for this week. In the previous lecture, we discussed about some introduction to block codes. That block codes actually belong to something that is called channel encoding or channel coding. And the purpose of using channel coding, or the purpose of applying channel coding to our message, is that because we want our communication to be more reliable. And channel coding ensures that the message that is sent from one point to another is actually received with more reliability. It provides a mechanism to detect some errors, and it provides a mechanism to correct some errors if it had the capability to correct such an error. So we studied about this introduction regarding channel coding in section 14.1 and 14.2, and today we are going to discuss the section 14.3, which is about linear block codes. So I said informed you earlier that there are several block codes or several channel codes actually that can be discussed, but we are only looking at this one specific channel code, that is the linear block code, because it provides a good understanding of how this process is going on. So as I said, you can also consult the book Bernard Saklar. I provided the link in the previous lecture to this book, and if you do, then you can obviously check out the section 6.4 to learn all about the linear block codes. And I recommend this chapter or this book for this specific topic because it has much more depth that is covered in some very short text actually. So it is good if you can study this topic from this book of Bernard Saklar. So in the previous lecture, we did discuss what is a systematic code and what is a non-systematic code. So just for revision, a systematic code is a block code, or is a code, actually a set of code words that have a code word which also includes the message itself. So when you generate a code word, and if you remember how you generate a code word, to generate a code word you multiply a message with a generator matrix. Okay. So when you get a code word, the code word actually includes the message itself. It's called a systematic block code. So if it does not include the message itself, it's called a non-systematic block code. To have a systematic block code, you need to have an identity matrix in the generator matrix. Okay. So this is an example where a generator matrix is given, and as you can see, there is no identity matrix that you can see in this generator matrix. So an identity can either be present at the end of this matrix or at the start of the matrix. However, you remember that the size of the identity matrix inside the generator matrix is every time it is of size k, or you can say k cross k, since it's a square matrix. So before we go ahead, I would want you to understand what is the value of nk in this problem that is in front of us. So as I told you that linear block code is expressed as an nk code. So what is the value of n and what is the value of k? So as you could see from here, that since the identity matrix has a size k by k, so identity over here can only look like a 3 by 3 matrix, because this is how you cannot fit a 2 by 2 matrix inside this generator matrix. You cannot fit a 2 by 2 4 by 4 matrix. So the only matrix that you can fit is a 3 by 3 matrix. So value of k must be 3. So this code must be of size 3 as the value of k. Okay. So what would be the value of n? So if you calculate the total number of columns in this matrix, which is 6, then this code is actually a 6-3 code. Okay. So actually you can always tell the size of the code just by looking at the generator matrix. So a generator matrix is always of size 3 cross 6, which is actually k cross n. So it has k rows and n columns. Okay. So when you see this generator matrix, you can easily see that the value of k is 3 because it has 3 rows and the columns are 6, which means the value of n is 6. Okay. So this dimension must be there in your memory to understand if this is a right generator matrix. The size of this identity should always be in your mind to make sure that the correct identity is represented. The size of parity bits that we discussed in the previous lecture should be there to understand if the parity bits are right or wrong, because for example we could write another column inside this matrix. For example, let's add 1 1 1. So now this becomes a 7-3 code actually. Okay, so you cannot just tell if this is the right matrix or wrong matrix. So if you are looking at this value and the value says it's a 6-3 code and you can see 7 columns over here, then something is wrong obviously. Either this value is wrong or there is an extra column inside. So you can make these adjustments or just notice if everything is correct that is available to you. Okay, so the size of G is fixed, it's always k by n, it's a k by n matrix. So we can see right now we have a 6-3 code, we have 3 rows and 6 columns. The size of the message is of 3 bits and the size of the code word is of 6 bits. Okay, so since we are saying that this matrix is actually a non-systematic matrix, it does not have an identity either at the start or at the end. Now we have to create a systematic block code, because we will only be discussing systematic linear block codes, because as we discussed earlier, it is more efficient to work with systematic block codes. Okay, so we can make a non-systematic generator matrix or a systematic generator matrix. Okay, so we can always make this conversion. To make this conversion, we follow the Gauss-Jordan elimination process, which you have already at least practiced once in linear algebra. So there are two operations that we can perform on this matrix to make it look like an identity matrix, either at the start or at the end. One is that you can either interchange any two rows. Okay, and the second application or second process that you can use is you can replace a row with sum of itself or any other row. Okay, so you can add two rows, you can uh, do some addition where two rows can be added. There is no concept of subtraction, because in mod 2 operation, addition and subtraction result in the same thing. So the only operation that we will use is addition, because we are using mod 2 operation calculations over here. Okay, so you can add any two rows, or you can swap any two rows or interchange any two rows. So let's try to make this generator matrix a systematic generator matrix. So if you can see some kind of hint of identity, then we can go ahead and make this an identity matrix. So I would like to make one observation. If you do notice this generator matrix, that you see 0 0 1 over here and 0 1 0 over here. Okay, so a generator matrix looks identity matrix would look something like this. Okay, and I can see the 0 1 0 and the 0 0 1. So these two things are already in the matrix. Okay, so let's make this adjustment to make sure that we get this identity in this correct format. Okay, so how do we do this? We will interchange row 2 and row 3. So these two rows can be interchanged to make it more look like an identity matrix. So once we swap these two rows, interchange these two rows, this is the result that we get. Okay, so we have 0 1 0 over here and 0 0 1 over here. However, if you notice, the top row right now is not in identity form. So how can we make this identity, which means how can we make this look like 1 0 0? So we need to convert this 1 into 0, and it can be converted if we add this row into this row. So 1 plus 0 would result in 1, 1 plus 1 would result in 0, 0 plus 0 would result in 0, and we will get this desired result. So we can add row 2 in row 1. Okay, so row 2 can be added in row 1. So if we do so, what do we get? This is the result of adding this row to this row. So 1 plus 1 would be 0, 1 plus 0 would be 1, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 0, 0 plus 0, 0. Okay, so we have this generator matrix now that has an identity at the end of 3 cross 3. Okay, so these must be the parity bits and this must be the identity. So we have an identity at the end and the parity at the start. This is the configuration of the matrix we have with us. Okay, so we have the generator matrix with us available now. So the next step that we can do is that once you have a generator matrix, you can always create the code words. Okay, and if you remember, code words can be generated with respect to the message. So if you have a message, you can generate a code word. Okay, so what is the message that is available with us? So if you remember the size of the generator matrix, the value of k is equal to 3. And if you remember, we were saying that 3 is the size of the message. So the message is of 3-bit size. So the message can look something like this, 3 bits. Okay, so the message is of 3-bit size, and using these 3 bits I can actually create code words of that are generated using these 3-bit messages. So I can create a total of 8 code words, as I'm doing over here. So there are a total of 8 code words, just as so. And if I have 8 code words, how many code words would I have? I'm sorry, if I have 8 messages, how many code words would I have? So 8 messages would create 8 code words. So if there's a question given to you that how many code words are there in this problem, obviously you have to calculate the total number of messages, and each message would correspond to a code word. Okay, so to get this first code word, you have to multiply it with G. So if you remember, message is multiplied with G matrix to get C code word. Okay, and again this is the matrix multiplication. So what is the size of M? If you notice, the size of M is 1 cross 3, 1 row and 3 column. And what is the size of G? It is 3 cross 7. So can we multiply M and G? Of course we can, because the number of columns in the first matrix or the vector is equal to number of rows in the second matrix. Okay, so we can make this calculation. And what would be the result of this multiplication? We would get another matrix, or you can say vector, or you can say, generally speaking, a matrix with a size that it will have 1 rows and 7 columns. Okay, so because it is only 1 row, that's why we call it a vector. So generally speaking, we call it a matrix, but for 1 row matrix we usually refer to it as a vector. So we will have an answer of 1 into 7 when we make this multiplication. So the code word would be of 7 bits. Okay, so this is the answer. So let's get the first code word. First we multiply this message with the generator matrix. So let's multiply, sorry, this is the generator matrix, systematic generator matrix. So we multiply the first code word with the generator matrix, and when we do, the first answer that we get is 0, all zeros, 7 zeros. Okay, so I'll let you know how I made this calculation. So you can obviously make this calculation. You can multiply 0 with this 0 plus 0 multiplied by this 0, 1 plus 0 multiplied by this 0, and this will give you the first bit. And for second bit, you will or the second component of this vector, you will multiply 0 with 1 plus 0 with 0 plus 0 with 1. So you will get the same answer as 0 again. So for 0 0 0, you will always get this answer. Okay, let's look at 0 0 1. So when I multiply 0 0 1 with this generator matrix, I do 0 into 0 plus 0 into 1 plus 1 into 0. So again I get a 0. Okay, so for this code word, this is the answer that I am getting. For the second value in this bit, 0 into 1 plus 0 into 0 plus 1 into 1. So the answer is 1. Again you have to perform mod 2 operation. Okay, so right now I have 0 plus 0 plus 1. So the answer is equal to 1. So over here I get an answer of 1. So for the third bit, 0 multiplied by 1, 0 multiplied by 1 plus 0 multiplied by 1 is 1. So the next answer again is 1. And if I carry on this calculation, the result that I will be getting is 0 0 1. Okay, okay, sorry, I just noticed that the value of this generator matrix is not 7, it is actually 6. So there are only 6 bits in the answer. So I added the 7th column by myself. It is not present in the matrix. So okay, we made a good observation that the answer would be equal to 6 bits, not 7 bits. So we have 6 bits in our code word. Okay, so this is 3 into 6. So I mistakenly wrote down 3 by 7 over here, there are 6 columns, not 7 columns. Okay, so good for a mistake, because we can make this adjustment now, we could notice it. Okay, so if you noticed earlier, then that is even better. Okay, so now I can write all these 8 code words, and you can see it is slightly time consuming, especially when you're doing it on a screen like this with a mouse. So on paper you can probably do it a little quicker, and if you're using MATLAB, a software such as a MATLAB, you can do it very quickly using some built-in functions to generate these code words. Okay, so what is the shortcut that I was using yesterday that allowed me to calculate these code words very quickly? So you know how we are performing the vector multiplication over here, but I was using a method that was giving answer very quickly. For example, for this message, when I multiply 0 1 0 with this generator matrix, so the result that I'll get would be 1 0 1 0 1 0. So this was slightly quick. So the reason that I'm getting this answer is there's a shortcut to this binary operation that we are doing. So with because in this calculation, what you can do is that you can notice the number of ones in the message. So right now I have only single one in the second column. Okay, so what you can do is, if I have the 0 in the first column and 0 in the third column, you can multiply those rows with 0, and that would be absent from your calculation. So the first column is 0, I'll multiply first row with 0. The third column is 0, so I'll multiply third row with 0, and only the second column or the second row is important for me right now. So since this is only the single row available with me, the answer is 1 0 1 0 1 0. So 1 0 1 0 1 0 is the answer, and this is the shortcut that I can use. Okay, so similarly, if I need to calculate the code word of 0 1 0 1, what will I do? I will multiply 0 1 0 1 with this generator matrix, and you notice only the first row is 0. So the first row is multiplied with the first column over here is equal to 0, so you multiply first row with 0, and the remaining two rows, the first and the second row, are in your calculation. So you simply add those two rows. Okay, and when I add those two rows, what do I get? 1 1 0 0 1 1. So the code word is 1 1 0 0 1 1. So 1 1 0 0 1 1. Now this is relatively a quicker way to compute the same calculation as I was doing previously. So to make these code words, the easier thing to do is just use those rows that have a corresponding 1 present in the column of that message. So for 100, so not exactly 100, sorry, should be said 100. So for 100, I multiply the first row with 1 and the remaining two rows with 0. So I multiply the first row with 1, and that's it. Other two rows are not important. So answer would be 0 1 1 1 0 0. So the answer is 0 1 1 1 0 0. So this is a lot quicker to do. So these are the set of 8 code words that I can have. I'm skipping these 3 code words, you can compute on your own. So these are the code words that I can get from the generator matrix. So this is what the generator matrix is for, and you have to remember the relation of generator matrix with K and N. It's a K cross N matrix. So it will help you in making the right calculations. So once you have G, you have the code words C. So whenever you want to transmit this message, instead of transmitting this message, you will have to transmit this code word to ensure that the communication is reliable. Instead of transmitting this 000, you have to transmit the corresponding code word to make sure that you have a reliable communication or channel encoded embedded in your message. Okay, so now we are transmitting the code words. So when we come at the receiver we have a parity check matrix, the H matrix. The H matrix would make sure that upon receiving this code word, we can detect or we can correct our received signal. Okay, so how does the H matrix look like? So we can calculate the H matrix using this computation that we already discussed in the previous lecture, that if a generator matrix has identity at the end, because we had an identity at the end, the start would be called the parity matrix. So in the parity check matrix, the parity would come at the end and the identity would come at the start, and you have to notice the difference in this value. Okay, so previously the size of identity was k cross k, now it is n minus k cross n minus k. So the value of n is 6 in our problem and the value of k is 3. So luckily that is again 3 by 3. So the H matrix would look something like an identity at the start, okay, just like this, and it is followed by the parity transpose. So whatever the parity was written in the G matrix, so whatever this parity is written over here, sorry, this one, the parity is written in the first 3 bits, in the first 3 columns, its transpose is written in the end of this H matrix over here, and that would make an H matrix. So this is how the H matrix would look like. Okay, the identity at the start and the transpose of the parity from the generator matrix. So now we have the H matrix. Okay, so as we discussed, the generator matrix is a matrix that is actually has some purpose at the transmitter, and the H matrix is a matrix that has its purpose at the receiver. So at the receiver sorry, at the receiver we receive a code word, and using the H matrix we check if the received code word has an error or not. Okay, so this is what we will do now. We will check if the received code word has an error or not. But before checking if the received code word has error or not, let's discuss one more thing. Okay, and that is called weight and distance of a code. Okay, so the weight and to calculate the weight of the code, it's a relatively simple process. We already have the code over here. So these are the code words. I've written only 5 code words. So let's just write down the other code words as well to make sure we solve the problem completely. So the next code word, if you can do the calculation with me, is 0 0 0 1 1 sorry 0 1. Okay, and the code word for this message is 1 1 0 1 1 0, and the code word for this is 1 0 1 and 1 1 1. So please remember, 1 plus 1 is 0 and 0 plus 1 is equal to 1. So 1 plus 1 plus 1 is equal to 1 in mod 2 addition. So these are all the code words. A weight of the code word means, so I am writing the weight over here, weight of the code word means number of non-zero elements or number of ones in a code word. So how many number of ones do we have over here? 0. How many number of ones do we have over here? 1, 1 to 3. We have 3 number of ones. So we have 3 number of ones over here. So we have 4 number of ones over here, and 3 number of ones over here, 2 over here, 4 and 5. Okay, so this is simply the weight of the code. Or again, if you want to discuss in terms of vector, we are saying a given vector contains or includes how many dimensions. So this one includes 3 dimensions. It is defined in 3 dimensions, so we say 3. So the weight actually is related to the size of that vector. However, we are not discussing vectors right now, so we'll satisfied with just the number of ones in the code word. So this is how you describe a weight of a code. So the weight of this code word is equal to 5 if we have this specific code. Okay, so the next thing is, once you calculate the code, the weight of the code, the next thing that you can do is calculate the distance, which is also called Hamming distance, and the weight is actually also called Hamming weight because all these names arise from the paper that are derived from Hamming's work. Okay, and we have a linear block code that is also called a Hamming block code, which we'll discuss later on. Okay, so this distance and the weight are also called Hamming weight or Hamming distance, or simply you can call them weight and distance as well. So we know what the weight is. Now we need to calculate distance. So to calculate the distance, and why do we need to calculate distance, is again because I would say that actually 2 code words mean 2 different vectors, and by calculating distance we are indirectly calculating the distance between 2 vectors. So we are calculating distance between 2 code words. So these are the 2 code words, okay, 101101 and 110110. So we need to calculate the distance between these 2 vectors. So how do we calculate the distance? actually we calculate the weight of their sum. Okay, so we add those two code words. If we add these two code words, what do we get? 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 0 is 1, then 1 plus 1 is 0, and 0 plus 1 is 1, and 1 plus 0 is 1. Okay, so I hope I've made the right calculation. 1 plus, let me just check it once again. 1 plus 1 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 0 is 1. Okay, so this is the right code word. So this is the sum of two code words. Okay, so the weight is actually equal to 4, not 3, but it must be a mistake. So its weight is equal to 4 because there are 4 number of ones in their sum. Okay, so this is the weight of their sum. The weight of the sum actually equals the distance between two code words. So to calculate the distance between two vectors, this is the indirect method that we are using. Okay, so now that we have computed the distance between two code words, we have to, in the problem, we actually have to calculate the distance between each pair of these code words. So there is a lot of distance to be calculated. Okay, so we have to calculate the distance between each pair. So these are just the 7 pairs I've made right now. First and second, first and third, first and fourth, first and fifth, first and sixth, and fourth and seventh, first and eighth. Okay, so then I have to calculate the distance between second and third, second and fourth, second, fifth, and so on. Then third and fourth, third and fifth, and so on. So there are a lot of weights to be, distances to be calculated between two code words. Now this is a lengthy process. So again we have a shortcut available with us, because what we are doing is that we are trying to calculate the minimum distance. So because we just calculated this distance, we are interested in the distance between two code words that has the minimum value. Okay, and luckily for us, the distance between or the minimum distance is actually equal to the minimum weight of the code word. Okay, so because we have already written the weights over here, the value of the minimum weight is actually equal to the value of minimum distance of a code. So we do not need to calculate all these pairs of the distance to see which one has the minimum distance. Luckily for us, the minimum weight is equal to the minimum distance between any two codes. So the minimum weight right now is 2, which means that the minimum value of the distance between any pair of code is equal to 2. So the minimum distance is 2. Okay, so luckily we do not need to make this long calculation. The weight is sufficient to make such calculation. Please note that this weight is not included, because the all zeros code word is always present in the linear block code. Okay, please remember this, that the all zeros code word is always present in the code word. Okay, so this is the all zeros code word, and since it will always be present in the code, its weight will always be equal to 0. So the minimum distance would always actually be equal to 0. But since the minimum distance involves distance between two vectors, so it's a distance between either these two or these two. So the minimum distance between any two vectors or any two code words is not just 0, it is a non-zero value, because I'm calculating distance between these two vectors. So this 0 is not an important value when calculating minimum distance, because it does not involve calculating the distance between two vectors. In fact, it's a value of just weight of this vector only, and the value of 2 over here actually means that the distance of this vector with this 0 vector is equal to 2, which is the minimum distance. Okay, so the minimum weight is actually sufficient to tell us the minimum distance, and indirectly it is actually telling us the distance between this vector and the 0 vector. Okay, so the minimum weight of a code word of the whole block of code is actually the minimum distance that is present inside that code. Okay, of course excluding 0, because 0 is not the possible minimum distance between two codes. Okay, so the minimum weight, the non-zero weight over here, is the minimum distance. So now we have a value of d min. So suppose the value of d min for a problem is equal to 2. okay, just like we had. So what do we do it to? Why are we interested in this value? Because once you calculate the value of the minimum distance, you can calculate the error correcting capability and the error detection capability of a signal. I'll just correct it. This is actually detection. This is not correction. Okay. So if we know the value of d min, you can calculate the code words detection capability, error detection capability, and code words error correcting capability. Okay. So how do we calculate this value? By calculating this value of t. So if you notice, the value of t is less than equal to 1 by 2 of d min, and this is a floor function. So if you remember floor function or ceiling function from a previous calculus course maybe, you will know that a floor function actually uh, eliminates or reduces the value of the decimal that is present. For example, if the value of a value is given to us that is 0.1, the floor will actually make it 0. And if it's a ceiling function, the ceiling function would make the value of 0.1 equal to 1. So it will increase the value to the next integer value, and the floor function will decrease the value to the next integer value. Okay. So since the value of d min for us is 2, so 1 by 2 into 2 is equal to 1, and the floor of 1 is equal to 1. It's already a decimal value, integer value. So the error detection capability is equal to the 1 bit. So we can detect a 1 bit error with these codes. Okay, so we can detect 1 bit of error with these set of codes because the d min is equal to 2. So obviously detection is one of the things that this channel code can do. The second thing that it can do is correct that error. So I'm sure you can understand that the natural capability of a code should follow the fact that if it has a detection capability of 1 bit, if it can detect 1 bit in problem, in error, it can at most or it can at best correct 1 bit as well. Now it cannot do that magic where it can detect 1 bit in error, but it can correct 2 bits. So that seems like a very strange property, and obviously it's wrong, that's not possible. So if I can detect 1 bit of error, then I can either correct 1 bit or maybe I cannot correct any bit. Okay, so this is a possible scenario, but this seems like a strange scenario where I have a detection capability of only 1 bit, but for somehow I can correct 2 bits. So it does not seem possible, seems a very strange phenomena. Okay, so the property says that I can detect 1 bit in error, and I can correct either 1 bit or less than 1 bits if the detection capability is of 1 bit. So this is the value of t for us. So how much is the error correction capability? So value of d min is 2, 2 minus 1 is 1, 1 divided by 2 is 0.5. So this floor of 0.5 is equal to 0. So as I said, this particular code cannot correct any error. It has a correction capability of 0 bit. So the code that we were studying over here has the capability of detecting 1 bit of error, but it does not have any capability to correct any error. Okay, so the error correction capability is equal to 0. Okay, so the error correction capability is of 0 bit, and the error correction detection capability is of 1 bit. So once we know all these backgrounds about the linear block code, the last thing that we can do is, since we are at the receiver end right now, and I paused a little while ago and I said that when we receive a code word at the receiver, uh, we can use H or the parity check matrix to detect if we have made an error or not. Okay, so how do we do it? So I left it over here. So let's start from here. The way I can do is that I can receive, if I receive a certain code word, I have to multiply it with the transpose of H. So let's take one dummy code word. Let's take this code word. Okay, let's put a star over here. So the code word is 110011 and the original message was 011. Okay, it's also present at the end of the code word because it's systematic. So 110011 is the code word. So 110011 is the code word. So I receive this code word. So when I receive it, I call it an R. Okay, it is the code word C, but when I receive it, I call it R because it might have an error. And if it has an error, obviously it is not equal to the code word. So generally we call it R. So the received signal is R. This is the message that I've received. I have to multiply it with the transpose of H. What if I try to multiply it with H? Again, that won't be possible because the size of R is 1 by 6 and the size of H is 3 by 6, and these columns and these rows are not equal, so I cannot multiply this. However, if I write it down as 6 cross 3, now the columns and rows are equal and I can do this multiplication, and the result will be equal to of 1 row and 3 columns. Okay, so let's just verify it. The transpose of H would be written as 1 0 0 0 1 0 0 1 0 1 0 1, okay, 1 0 1, and lastly 0 0 0 1 1 1 1. So this is HT. So again, I'll use the shortcut of this multiplication. First, second, fifth and sixth rows are important for me. So first, second, fifth and sixth rows are important for me. I'll just add these three values. So when I add those, 1 plus 0 is 1, 1 plus 1 is 0, 0 plus 0 is 0, the first value is 0. So 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0. So again, if you notice, the answer is of 1 cross 3, which is true for what we said, that the answer would be 1 cross 3. So 1 cross 3 is the answer. So this is the answer 0 0 0. So what does this answer tell us? This answer is called the syndrome. So the syndrome right now is 0 0 0. Okay. So if a syndrome is 0, or it's a 0 vector actually, then we say that the received code word is the correct code word. However, if the syndrome is non-zero, then we say that an error has taken place. Okay, and we may be equal to correct it. For example, in this case, let's discuss this example. Supposedly I receive 0 1 0 0 1 1. Okay, so now I have one bit of error over here. The received code word got corrupted. It is 0 1 0 0 1. So now if I do the same calculation, the answer that I'll get is second, fifth, sixth row important for me. Second, fifth and sixth row is important. 0 1 0 is 1, 1 0 1 is 0, 0 1 1 is 0. So this is the answer, 1 0 0. So 1 0 0 is the answer. This syndrome is non-zero. This means an error has taken place. So can I correct this error? No, because if you remember, this code has 0-bit capability of correcting an error. However, it did have a capability to detect one bit of error, which it did, because as it showed me a non-zero syndrome. So the detection capability was there, but the correction capability is not there, so I cannot correct this error. So this is how we use linear block code to encode a message, channel encode a message, and then at the receiver, using the parity check matrix, decode the message and try to understand by looking at the syndrome if an error has taken place or not, depending upon the capability of my code, if it can detect or it can correct the error.